Welcome to GER Hub. Welcome to our class. Sorry for the delay. It was due to several technical issues. Thank you for nevertheless staying tuned to the class. So welcome from every part of the world. We are discussing set theory. We would continue our discussions on set theory in today's class. So previously we've had two classes on set theory under MTH 101 as it is in my school. I don't know how it is in your school, but this is first semester undergraduate mathematics. So please, if you are watching, do well to drop your good comments and also subscribe to the channel if you haven't subscribed, and let us begin. So this will be our third live class on set theory. Okay, so this is our third live class on set theory. Sorry for the delay. So quickly, without much waste of time, let us begin. Let's begin our class today. So previously, what we discussed on set theory were the following. So far, so good. We have discussed the following. I'm going to put the link to the first class and the second class we've had on set theory in the description below. So if you want to go to the first class and watch what we did, you can check the link in the description below after this class. If you want to visit the second video we made, you can also check the description after this class. Please, as you come in, drop a like and make yourself known. Let us know where you're watching from. So please, you could do that by just telling us your name and where you're watching from, okay? That will be a very good one. So let's start this class with the following. A reminder of what we have done previously. So I'm going to put here reminder, okay? So let's remind ourselves of what we've done so far in the first and second classes, okay? In the first and second classes we had. So the first thing we discussed was definitions. We looked at definition of sets. We also considered what is not the definition of a set. We considered that in our first class. We went on in our second class, still in the first class, we went into description of a set. We went into set description of a set. We discussed that these were the items we discussed in our first class. So this was our first class. And for you to watch the full video, please check the description, the link in the description after this class. Now, in our last class, being the second class on set theory, we focused on remarks and definitions. So definitions, not of sets, but definitions in set theory and remarks. So only that we had to stop that class due to technical issues. We were to discuss another thing. Apart from definitions in set theory, we were also supposed to discuss set operations. So we couldn't take this. We have been able to do a little bit about this. So this is incomplete. That's where I'm going to start from. We have done this. We have done this. We have treated this. We have done this incompletely. So I'm going to start from definitions in set theory and remarks, and then move over to set operations. Now, please take note. We have been able to discuss remarks. We considered several remarks in that class yesterday, and we were taking these but did not complete it. So this is where I'm going to begin from. So let's quickly look at the definitions we had taken in the last class. So under definitions, what did we look at? So the class of yesterday, in which we took definitions in set theory and remarks, began with me going through several remarks. Remember, if you've watched the video of yesterday, you would notice that the remark number 1 told us yesterday that sets are generally represented with capital or uppercase letters, except specified otherwise. So wherever sets are discussed, whenever set is discussed, it is always described using capital or uppercase letters. Now, if you want to use any other symbol or letter to represent a set, then you would have to specify that. You would have to make us know that you are going to be using this symbol or that symbol to represent a set. Otherwise, conventionally, that is all over the world as agreed, sets should be represented with uppercase letters. That was our remark number 1. For remark number 2, whereas sets are represented with uppercase letters, the elements in a set are represented with corresponding lowercase letters. Not in all circumstances, however. This means that if a set is represented with uppercase A, then its element is properly represented with lowercase a. Okay? So if uppercase A represents a set, what is proper, although not compulsory, is that lowercase a should represent the elements in the set. And we said also that the element in a set, which is regarded as the object in a set, can also be called member of a set. If you don't want to call it member of a set, you could also call it component of a set. So objects of a set or in a set may be called elements, they may be called members, they may be called components. And that was remark number 2. Going to remark number 3, we said in yesterday's class that symbolically, you could use a, you could use certain symbols to represent statements, to make statements in set theory easy. For instance, if you want to say that A is an element A is a member of, if you want to say an element A is a member of a set A, it is simpler to write it in set theory as A is a member of A. And I told you in yesterday's class that this symbol stands for membership. The symbol is called the membership symbol, and it means that A is a member of A, the set A. Now, just like you have the membership symbol, we said yesterday that you also have what we call the non-membership symbol. How do you form the non-membership symbol? All you have to do is to use a stroke to cross the membership symbol. So whereas this symbol is called the membership symbol, this symbol is called the non-membership symbol. Okay? So now we moved on from that particular remark to remark number 4. In remark number 4, we said that set elements are always enclosed in what we call curly brace, a curly brace. So it means that in set theory, we don't use this kind of bracket for sets to contain the elements of a set. Neither do we use these parentheses. We rather use what we call a curly brace. So if you want to specify the elements in a set, you put all of them in this type of bracket or brace. So this type of brace is called a curly brace. So we don't use this, neither do we use this. The proper thing to use to show the elements or to contain the elements of a set is this one. Then we moved on from there to remark number 5. In remark number 5, we say sets are unique and distinct. And I took my time yesterday to explain what that means. It means that for you to say sets are unique, set elements are unique and distinct, means that in a set, repetition is not considered or put in topmost priority. For example, if you have 2, 5, 5, 4 as a set, 5 and 5, although repeating twice, is regarded as 1 in a set. So it is the same set as writing 2, 5, 4. That is how we observe or consider this set, irrespective of the fact that 5, an element of the set, repeats itself twice. So set elements are unique and distinct. And that means, number two, that this set 2554, which may be written as 254, is the same as ordering them as 245. So irrespective of how you place the elements, provided the elements are in another set are the same as this one, they remain the same. What that means is that the set 254 is the same set as the set 24 containing 2, 4, and 5. So order does not matter, neither does repetition matter. That brought us to the end of remark number 5. So after our remarks in yesterday's class, we now moved on to the definitions. We moved on to definitions. The first definition we considered in yesterday's class was definition number 1, what it means when we say a set is finite. So we explained what a finite set is in yesterday's class under definition 1, and we said a finite set is a set whose elements are countable and exhaustible. Please take note, you can go over that video to watch the explanations. We went on to definition number 2, where we discussed infinite set, and we said an infinite set is a set whose elements are countable but inexhaustible. We now went on to definition 3, which was about countable sets. And we explained what a countable set is so that it should not be confused with what a finite set is. We now went on to explain an uncountable set. So if you want the details of these things I'm mentioning, go over yesterday's video. So I will put the link in the description below. Then we now went on to definition number 5. And in definition number 5, we started discussing the null set. And that was where our class ended yesterday abruptly because of technical issues. So I'm going to start with definition number 5. So please welcome to the class. So we are considering set theory class 3. Okay, this is the third class on set theory. So that being said, let us now see definition number 5. So in definition number 5, let us reconsider again the null set. So what is a null set? I started with saying that a null set is also called an empty set. A null set is also called an empty set. That is the first thing I said yesterday. More so, I told you, calling a null set an empty set is not a definition. So the question is, what is a null set? A null set is a set that contains no element. It is a set that contains no element. Okay? So that is the definition of a null set, otherwise called an empty set. So when a set is null or empty, it means it contains no element. In set theory, we use these symbols to represent a null set. So we said a null set may be denoted using the symbol phi. That is this symbol. The name for this symbol is phi. Okay, so you either may be using phi to denote a null set, or what we call an empty brace, an empty curly brace. Empty curly brace. So these are two symbols used for representing a null set. Okay, remember we've said three things here. A null set is called an empty set. A null set is a set that contains no element, and a null set may be represented with either the symbol called phi or an empty brace. Now please take note that if you say a set is empty and you end up using this symbol phi, which is an empty set, putting it into this brace, this curly brace, this is not the definition of a null set. So please take note of that. This set that contains phi as an element in it is not a null set anymore. If you want to tell us that a set is null, use this symbol or use this symbol alone independently, you will be referring to a null set. That was definition number 5. Now let us go over to what I'm going to call definition number 6. Definition number 6. And definition number 6 is about a set we call singleton. If I were to be in class, I would be saying my students should repeat that word again because it is often very pronounced wrongly by students. The word is singleton. So the question is, what is a singleton in set theory? I'm going to start with saying a singleton is a set that contains only one element. Only one element. So guys, any set that contains only one element is called a singleton. Examples of singletons. Let's take examples of singletons. So if I have a set A that contains orange as the only fruit, because orange is an element in that set A, making it just one element in the set. This set, because it contains one element, is called a singleton. Please, there is nothing like singleton set. Okay? It is either you say the set is singleton or the set contains one element. Please. So singleton set, avoid the use of this language. Just call it singleton. Okay? So a set that contains only one element is called a singleton. Another example of a singleton could be the set B that contains this all x that are natural numbers, okay, such that x lies between 0 and 0 and 2. So this set amounts to 1. Okay, this, remember, under our set theoretic notation, I told you that this will be read as the set B is the set of all elements x. This bar is read as such that. So the set B is the set of all elements x such that x is a member. Remember, this is our membership symbol. X is a member of this type of n, stands for natural number system. This n here, wherever you see it, guys, all over the world, it stands for natural number system. After this topic, the next topic we'll be moving into will be number system. So there, I will be explaining the different types of number system. But take note, wherever you find this type of n all over the world, it stands for natural number system. So natural numbers are positive whole numbers. So if we are discussing singletons and we have said that a singleton is a set that contains only one element, please take note of the fact that this set will give us a singleton. Why will it give us a singleton? It is because the only natural number that lies between 0 and 2 is 1. I repeat, the only natural number, if we have said B is the set of all elements x, such that x is a natural number, remember, comma is read as an in set, and x lies between 0 and 2, then it means that the only natural number, since natural numbers are positive whole numbers, the only natural number that lies between 0 and 2 is 1. For that reason, because of this result, which goes with the definition of a singleton, this set is a singleton. So B is a singleton because it contains only one element, which is 1. A last example on singleton is a set like this, a set that contains just Toyota as a car, a brand of car. Okay, so C equals Toyota means it is a set that contains only one type of car, Toyota car. So please take note, provided a set contains one element, then it is called a singleton. That being said, let us move over to definition number 3. Let's move over to definition number 3. So for definition number 3, definition number 7, sorry. So let's move over to definition number 7. So for definition number 7, let us now consider yet another definition that is important in set theory. It is the definition we call the definition on subsets. Okay? Subsets and supersets. Okay? So, what is a subset? What is a subset? So, I'm going to say, let A be a set and let B be another set. Let A be a set and let B be another set, such that every element in A is found in B, and every element in B is found in A. Then the set A can be called a subset of B, and the set B can also be called a subset of A. Let me explain this, please. Remember the statement. So I'm starting with giving you two sets. There are two sets here. One set is A and the other set is B. Okay? One set is A and the other set is B. Thank you very much, my love. One set is A and the other set is B. Now, if we have two sets such that every element that is found in the first set is also found in the second set. Okay? So if I have, for example, let me make it very clear. If I have a set A such that this set contains 1, 2, and 4, and I have another set B such that B contains 4, 2, and 1, these two sets, because 1, 2, and 4, which are elements of A, are found in B, and 4, 2, 1, which are elements of B, are found in A, we say that A is a subset of B and B is also a subset of A. In this case, we use this notation. We say we would use this symbol. A is a subset of B and B is also a subset of A. Okay? So this symbol here, guys, this symbol is called subset notation. These two symbols are called what? Subset notation. Okay? You use them. In this case, please take note. I'm going to explain a different thing just now. In this case, please take note. There is a thing that looks like a C with an equal to underneath. If I remove the equal to, what it would mean is that A is no longer just a subset of B. It is now what we call a proper subset of B, and I'm going to explain that. However, when it contains an equal to as it is here, please take note that it means that every element you find in A is found in B, and every element you find in B is found in A. So, what if it so happens that A contains element 1 and 2, and B contains yet again 4, 2, and 1? In this case, when A contains elements, all of which are found in B, but there is at least, that is, one or more elements in B that are not found in A, just like you have it in this case. In this case, A contains 1 and 2, and B contains 4, 2, 1. The missing element in A that is not found, that is found in B, is 4. Now, it now makes it look as if all that is in A is completely in B. In that instance, we say A is a subset, a proper subset of B, and we remove the equal to from underneath the symbol above. We leave it in this manner. This particular one will read A is a proper subset. A is a proper subset of B. The proper there means that there are elements in B, the bigger set, that are not found in A. That is what the proper means. But when it so happens that all the elements in A are found in B and all the elements in B are found in A, this is the proper notation to use. And in that case, A is said to be a subset, just a subset of B, in the same way B is just a subset of A. But if it happens that there are some elements in B that are not found in A, making B the bigger set and A the smaller set, then we say that A is a proper subset of B. Now, if you want to use this statement in reverse, if you don't want to say A is a proper subset of B, you would rather say there is a symbol, you would turn this symbol to the left, okay? You will turn this symbol to the left so it now looks like this. Instead of going this way, it now goes this way. And in this case, we will now write B A with the symbol in between, and it will no longer read B is a subset of A. Rather, we would mean B, this will read B is a superset to A. The reason why B is a superset of A or to A is simply because it contains more elements than A, even as it contains all the elements in A. So please take note of these differences. What is a subset? A subset is a set that contains elements that are found in the other set, in another set. Okay, all of which are found in the other set. So please take note of that. Now, that being said, let us go over it quickly again. We started with saying that let A be a set and let B be another set, such that every element in A is found in B and every element in B is found in A. Then A is called a subset of B. So I'm going to put here, I'm going to make a remark here. However, if there exists some elements, if there exist some elements in B not found in A, then A is said to be a proper subset. A is said to be a proper subset of B, while B is called a superset of A. So it is as easy as that. Now let's take some examples on definition 7. Superset, subset. Let's take some examples. Now, let's do this together, everybody. Let's do this. Now, look at these sets. I have a set A that contains 1, 2, 3. I have another set B that contains 3, 4, 5, 1, 2. I have another set C that contains 1, 2. Yeah, good evening, Isaac, Ayambe. Welcome to class. Thank you very much for your comment. I really appreciate it. Thank you. Please drop a like on the video. Please, if you understand what is going on, let me know. If you have any question, ask in the comment section. This is a live class. Just as you could have your class in the physical space, this is a live class. Just feel free to ask any question, okay? And I will answer. I will see your comment and I will reply them. Thank you very much. Now, let's look at this. Let's use these examples to explain what we have just said. So I'm having a class, I'm having a set here that contains 1, 2, 3, 4, 5, 6, 7, and 8. Okay? Now, if I want to use the subset notation, the superset notation, let's also add one set here, one more set D that contains 3, 1, and 2. Now, let's start with number 1. I won't be wrong to say A is a subset of D and D is a subset of A. This will be correct. The reason why this will be correct is because remember what we said about our remark on set, that set elements are distinct and unique. Take note, A contains 1, 2, 3, D contains 3, 1, 2, the same element, irrespective of the order, they are the same set. So A contains, yeah, Isidore. I hope I'm getting your name right. Isidore. Good evening. Good evening. Welcome to class. Please feel free to ask a question if you have one. Thank you very much for joining in. I can see you clearly. Now, so A is a subset of D and D is a subset of A is a correct thing. Simply because A contains elements that are found in D completely and D contains elements that are found in A completely. So this is the correct notation to use. A is a subset of D and D is a subset of A. Now, another conclusion we can get from that example is that A is a proper subset. Take note, A is a proper subset of B. The same A is a proper subset of C. Okay, so A is a proper subset of B and A is a proper subset of C. Mode Ayabom, I hope I'm pronouncing your names correctly. Welcome to class. Good evening. I'm really happy to have you too. So please take note. A is a subset of B. Why is it a proper subset? I am using the language proper, and take note of my notation. There is no equal to underneath. It is because I am removing the equal to, because at no in A found in B and all the elements in B found in A. So you only have, there are some elements missing from A that are not in A rather, but are in B. So A is a proper subset of B. In the same way A is a proper subset of B, please take note. Precious O2, welcome to class. Thank you very much. Thank you for your support. Thank you and welcome to class. Just please pay attention and ask questions where necessary. I will answer your questions. I hope you guys are following. If you are following, please just tell me I'm following in the live comment. Okay, just tell me I'm following. I understand. If you understand, if you don't understand anything, let me know and I will explain. So now D is a subset of B. Rejoice Gabriel, welcome to class. Thank you very much for joining the class. Good evening, sir. Yeah, one of your students from information system. That's nice. That's what I really want. So when you join in, tell me where you are watching from, what department. I really appreciate that. It makes me know who really supports the channel, who is supporting our video, and who is attending class. Thank you very much. I'm grateful. Now, I want to ask a question, guys. Is this statement correct based on what I've explained? Is D a subset of B, a proper subset of B? And also, is D a proper subset of C? Question mark, question mark. Please let me know. Is D a proper subset of B? Is D a proper subset of C? Remember, a proper subset is, D will be a proper subset of B if it contains elements in B rather. D will be a proper subset of B if it contains elements that are found in B, but there are some elements in B that are not found in D. So let me know if this is correct. To the best of what I've explained, this is correct. Okay, so please, Routine Okori, welcome. Thank you very much. Yes, you are following. One of your students from statistics department. Thank you very much. Okay, so let's move over to number 3. Another conclusion we can draw from this example. You will notice that B is a proper subset of C. You will notice that B is a proper subset of C simply because the set B contains elements that are found in C, but there are some elements in C that are not found in B. For instance, in B, you have 3, 4, 5, 1, and 2. And there is no 8, there is no 7, there is no 6. But these are elements found in C. It means that Daniel Abam, welcome. That's my class rep. Yes. Welcome. Thank you very much. Okay, so in C, there are some elements in C that are not found in B, making C a bigger set than B. Okay, so if you find out that all the elements you have in B are completely found in C, but there are some elements in C that are not found in B, then C can be called a superset to B. In other words, B is a proper subset of C. So this is correct. Okay, now number 4. Question is C a superset? Are we right to say C is a superset to B? Yes or no? If yes, please write yes in the comment section. Are we correct to say that C is a superset to B? Question. While you are thinking about that, let me put another one. Number 5. Are we correct also to say B is a superset to A and B is a superset to D? Are we correct? If we are correct, let me know in the comment section. Yes or no? Just type yes or type no as the case may be. Now, truth be told, we are correct to say C is a superset to B because it is a bigger set than B that contains all the elements in B, having some elements in itself that are not found in B. So these are correct. Okay, these are correct. Now, Moving on from there, let's go to definition number 8. Remember what we are discussing. This is our third live class on set theory. If you want to understand, yes. Thank you very much, Daniel Abam. Thank you very much. So I believe you understand. Now let's go to definition number 8. Definition number 8. What we are doing in this class is to take definitions we need in set theory. That's what we are doing in this class. So we are looking at definitions in set theory, and we are also going to begin operations in set theory. So the next definition is called the universal set. The universal set. Okay? So the symbol for the universal set, let me start from there. The symbol for the universal set, is either this or this. Okay? So the symbol for the universal set is either of those in the university also. So thank you very much for staying tuned, irrespective of that break in transmission. Now we are looking at the universal set. So definition of it. The symbol for the universal set is either this symbol or this symbol. Okay? So if you want to represent the universal set, use this symbol or this symbol. Two of them could be used to represent the universal set. But now the question is, what is the universal set? So I'm going to say the universal set is, thank you very much, John Bless Fortune. Thank you very much. Sorry for the break in transmission. My daughter was disturbing that she wants to come in. She wants to learn with you guys, and she's here learning right now. So if this were to be the physical space, you would have the opportunity of welcoming her. She wants to be an undergraduate, even in nursery school. So sorry for that distraction. Now, the universal set is the largest set. It is the largest set under consideration in a set problem. So it is the largest set under consideration. Please take note, the universal set is not just the largest set. It is the largest set under consideration. So you don't say the universal set is the largest set and stop the definition there, because it may not, you could call a set the largest set, but because it is not the set under consideration, it is not the universal set. If it is the universal set, it must meet the criteria of being the largest set. Welcome, yes, from biochemistry, John Bless Fortune. Thank you very much. Samuel Ina, thank you very much. Welcome. I'm really enjoying the fact that you guys are turning up in this class. I'm grateful. I really appreciate it. God bless you all. So the universal set is the largest set under consideration. Guys, I am saying the universal set is not the largest set. Don't stop your definition there. It is the largest set under consideration, meaning that if you stop your definition at saying that the universal set is the largest set, then the question is it the largest set under consideration? If it is not the largest set under consideration, then it is not the universal set. So a set can be the largest set, yet it is not the set under consideration. So what makes it the universal set? It is not just being the largest set. It is being the largest set under consideration, and it can be represented with this symbol or this symbol. Okay? So that being said, let us now move over to an example. So let's see this. Let us now assume this in this example. Excuse me. So let's assume we have this example. I have a set A that contains 1, 5, 2, and 7. And I have a set B that contains 1, 2, 3, 10. What do you want? What? Paper. Take this one. This one. What do you want? This. This one. This one. Okay, sorry about that. Now, let's look at this example to explain the universal set, guys. Let's look at this example. So, we have A containing 1, 3, 4, 5, 2, 7. We have B containing 1, 2, 3 to 10. And we have C containing 1, 2, 3 to 20. Now, out of these three sets, if I have a set problem, let's assume that these three sets are involved in a set problem. Now, which out of these three can be called my universal set? Out of these three, if I am considering these three sets, the set that is largest out of my consideration is the set C. So it means that C is my universal set because C contains elements 1, 2, 3, 4, 5, 6 down to 20. B contains 1, 2, 3 down to 10. And A contains 1, 2, 3, 4, 5, and 7 as elements. So I am saying that your universal set is the largest set under consideration. It is the largest set under consideration. And in this particular case, guys, out of the sets A, B, and C, if we are considering them, if we are considering these three sets in a set problem, which one will you call your universal set? The one that you would call your universal set is the set C, because it is now the largest set out of the three sets considered. So it is the largest set under consideration. Okay? That being said, let us now move to a next definition. Let us move to the next definition. Equality of sets. So definition number 9. Definition number 9. What is it? Carry it. What do you want? Okay. Take. Don't disturb my class again. Sit down here. Thank you. Tell me thank you. Thank you. Good. So definition number 9, guys. Now for definition number 9, let us look at equality of sets. So let A and B be two sets. Then A and B are said to be equal. A and B are said to be equal if all the elements in A are found in B, and all elements in B are found in A. So if every element you have in a set, if you say two sets are equal, for example, set A and set B. Set A and set B are only equal. Please, I repeat, only equal if and only if every element you find in A is found in B. If all the elements you found in A are found in B, and all the elements in B are also found in A, then we say that A and B are equal. We write this as A is equal to B. Okay? We write it as A equals B. So please take note, A equals B means all the elements in A are found in B, and all the elements in B are found in A. So mathematically, if you want to write this is what we do. If you don't want to write this definition in statement form, just like we've written it, what we do is this. We will say that A is equal to B. A set A is equal to B if and only if an element X being a member of A implies that this symbol is called an implication symbol. Please take note. And I'm saying if you don't want to write this definition in English the way we write it here, please take note, we can write it mathematically in this manner. A is equal to B if and only if. IFF means if and only if. It is a biconditional statement. If and only if X is a member of A implies that X is a member of B, and X is a member of B implies that X is a member of A. So this is the mathematical way of stating what we have written here. So if two sets are equal, it means that they contain the same elements. Let us leave the big grammar. Let us leave the big mathematics. Let us put it in simple terms. If two sets are equal, they contain the same elements. For instance, if A is equal to B, then it means that if A contains 1, 2, 3, then B would also contain 1, 2, 3. Even if B is written as 3, 1, 2, it is still the same set as A. They contain the same elements. Okay? Now, let's go to another definition. Definition number 9. Let's go to definition number 9. So in definition number 9, let us look at what we call power set. Let's look at what we call the power set. Okay? What do we call the power set? Definition number 9. Okay, that should be definition number 10. This is now definition number 10. So, power set. What is a power set, guys? The power set of a set A, take note, is denoted. There is a symbol for representing power set. Samuelina, for me, being known, I'm a student. Okay. So you are an information system student. Thank you very much for joining the class. So the power set of another set A is denoted as P of A. So we use P in bracket A to stand for power set of a set A. So every set can have a power set, what is called a power set. Every set can have what is called a power set. So the power set of a set, say A, is denoted as this. Some textbooks would even put it as this. Some textbooks will use row A. Whichever one, whether this or this, wherever you see it in set theory, it means power set of A. So the same way you have power set of a set A, you can also have power set of a set B. You can also have power set of a set C. So this is P of A. You can read it as P of A means power set of A. P of C, or this is P of B, so power set of B. And P of C will be read as power set of C. Okay? So, what is the power set of a set? Now that we know that it is denoted by this symbol or this symbol, the power set of a set, the power set of a set, say A, is the set which contains all the possible subsets, of the set A. Okay? Now, I'm going to show you how to get this done. The power set of a set A. Let's take an example now. Remember, the definition says the power set of a set, say A, is the set which contains all possible subsets of a set A. Now, before we go further, take note, as a rule, the power set, the empty set that we discussed earlier, the empty set this, and the set itself are always subsets. They are always subsets of the power set. So if you want to form the power set of a set, please take note. You would call all the sets that make up that set, including the empty set and the set itself. Okay? So it is very easy to form the power set of a set. I'm going to teach you right now how to get that done. So let's assume, as an example, let's assume that we have a set A, and the question comes, let's assume that we have a set A that contains 1, 2, and 3. Okay? Now, the question says, find the power set of A. So if this question demands that you find the power set of A, how many elements do you have in A? 1, 2, and 3. Now, all you would have to do is to say P of A meaning power set of A, according to the definition, says that the power set of a set is the set which contains all the possible subsets of A. Now, for you to form the power set, you have been told in the second remark that in any power set at all, the set itself and the empty set are always members. So this one has helped us with an expo. So I'm going to put the empty set as a member of my power set and the set A itself as a member of my power set. So I've put them there. Now, what would I put next? You will start with taking the singletons. Remember, we said a singleton is the set that contains only one element. Now, in A, I have 1. Please, when you are writing 1 as a subset of the power set, you put it in a curly brace because in the power set, it is a set. Okay? But in A, it is an element. Please take note. You don't write 1 in the power set without putting it in the curly brace. You will be wrong. So when you want to start listing out the subsets that make the power set of a set, I am saying put 2 there. To start with, put 2 sets. The empty set is a member of the power set. The set itself is a member of the power set. Then start mentioning the singletons, the set that contains only one element. So the first singleton is 1. The second singleton is 2. The third singleton is 3. Then I will now move from the singletons. I will move over to the duals, the set that contains 2. I'm going to start with 1 and 2. 1 and 2, I will put them here. I will go over to 1 and 3. 1 and 3, notice, is a subset of A. 1 and 2 is a subset of A. 1 is a subset of A. The set that contains 2 alone is a subset of A. The set that contains 3 is a subset of A. The empty set is a subset of A. The A itself is a subset of itself, like we explained earlier under subset. Then the last element here that completes this power set is the set 2, 3. Now, notice something, that in the power set of A, whereas A contains 1, 2, 3 elements, its power set contains 1, 2, 3, 4, 5, 6, 7, 8 subsets. Now, you will see quickly that there is a mathematical relationship here. The power set of A is 2 raised to the cardinality of the power set, 2 raised to the cardinality of A. And that brings me to definition number 11, side by side. I'm not done with power set, but let us now see definition 11 because we need it. So definition 11. Definition 11 is all about what we call cardinality. If you were to be in class, I would ask you to repeat this after me. Cardinality of a set. What is the cardinality of a set? What is the cardinality of your class? What is the cardinality of your home? What is the cardinality of your church? Guys, the word cardinality in set theory means number of elements in a set. So if, for example, there are 4 boys in a room and they are related such that we can call their collection a set, then because it is a set, the cardinality of that set simply means what is the number of elements in that set. Thank you very much, Sophie D. Thank you, Priya Patrick. Thank you, Samuelina, for staying tuned to the class. So I'm saying that the cardinality of a set is the number of elements in the set. So the cardinality of a set refers to the number of elements, Okay, my name is Precious from Information System. Thank you very much. But the name I'm seeing here is Sophie. So your name is Precious. Thank you very much, Precious. Welcome to the class. Please, all of you joining the class, drop a like on the video. I really appreciate it. And if you have not subscribed to the channel, please just click subscription. Click the subscription button. Just click subscribe there. Okay. Thank you very much. Yes. So thank you, Crystal Sculptor. That's my wife. Okay. So the cardinality of a set refers to the number of elements in the set. So let's assume that there are 4 boys in a class. If there are 4 boys in a class, the cardinality of this class will be 4. If there are 8 oranges, if there are 8 oranges in a basket, if there are 8 oranges in a basket, then the cardinality of the set containing these oranges will be 8. So please take note, we use this small letter n. Let's call this set that contains the 4 boys A. Let's call this set that contains the oranges, the 8 oranges, B. Then, for us to say the cardinality of this set is 4, we write it simply by putting small letter n in bracket capital letter A and put there equal to 4. For you to say the cardinality of this set that contains 8 oranges is 8, we write it mathematically as small n, put a bracket, put your B, the set inside, and put equal to 8. So cardinality means the number of elements in a set. Now, let us go back to definition number 10. Now that we've done justice to that, let's go back to the power set. I was not done with the power set because I needed explanations from cardinality. Now, look at it this way. I am saying, okay, thank you very much. Thank you for understanding that. So, now that we know that the cardinality of a set refers to the number of elements in a set, let's now conclude this class until tomorrow's class with the definition of a power set. We have said that a power set is denoted with this symbol or that symbol. Story number 1. Story number 2. A power set of a set is the set which contains all the possible subsets that you can get from that set. Now, take note, the rule says that the empty set and the set itself are always members of the power set. So let's now see. If I want to form a power set, let's say we have a set A that contains 1, 2, 3. I'm saying for you to form the power set of A, you write it in this manner and put equal to, you will start with, I usually like starting with the empty set because I know that the empty set is always a member of any set. Now, how do you know that the empty set is always a member of any set? When all of you leave your classroom, the empty set is there. It will be, your class becomes empty and the empty set is always present. Okay, so that's one analogy. Just look at it from that angle. The empty set is always a member of any class. When all of you leave your class at the close of lecture, the class is empty and the empty set is a set, so it is always there. Number 2, when all of you are full in the class, you are a subset of yourself. So if the set is A, it is a subset of itself. So once you put those sets, those two sets, you now start with mentioning the singleton. I am saying that when you list out the elements of a power set, please take note that the elements of a power set are sets themselves. So you have to put them in curly brace. Whereas in the set, it is 1 in this manner. In the power set, it has to be in the curly brace. So 2 is another subset of this set. Remember, the power set is a set that contains all the possible subsets of a set. 3 is a subset of the mommy is okay, I'm having a class. 3 is a subset of the set A. Then go to the dual set. 1 and 2 is a subset of A, so it goes in here. 1 and 3 is a subset of the set, so it goes in there. And finally, 2 and 3 is a subset of this set. So in this set, I can draw the subset 1 from it. I can draw the subset 2. I can draw the subset 3. I can draw the subset 1, 2. I can draw the subset 1, 3. I can draw the subset 2, 3. I can draw the subset, the empty set, and I can draw the subset 1, 2, 3, which is A itself. Okay? So now, if you look at it, a set that contains 3 elements gave us a power set that contains 8 subsets. So what I'm saying is that, take note, A, the power set of A is 2 raised to the power of NA, the cardinality of A. Now, the cardinality of the power set is 8. Look at it. 1, 2, 3, 4, 5, 6, 7, 8. The cardinality of our power set is 8. And how did we get that 8? 2 raised to the cardinality of the set. The set contains 3 elements, 1, 2, 3. So 2 raised to power 3 is 8. Now, it means that in your exam or in a test, If I tell you that a set B contains two elements, small a and small b, how many elements will its power set contain? The relationship is n. The cardinality of the power set of B will be equal to 2 raised to power the cardinality of B. And in this case, it will be 2 raised to power the cardinality of B, which is what? The cardinality of B is 2. There are 2 elements in B. So this will be 2 raised to power 2, giving me 4. Now, if we ask you to produce the power set of B, all you will do will now be all you will do is to do the following. So PB will be the set that contains the empty set. Remember, the empty set is always there. The set that contains B itself. So the two of them must always be there, the empty set and the set itself. If you are asked to form the power set, then you will now put the singleton. The singleton is A and the singleton is B. So these are 4 elements that are contained in that set. What if I gave you a set C that contains I, E, A, B? This set contains 1, 2, 3, 4 elements. So its power set, the power set of C, will contain how many elements? The empty set, number 1. The set C itself, number 2. It will contain I as the first singleton. It will contain E as the second singleton. It will contain A as the third singleton. It will contain B as the fourth singleton. It will now contain the duals, which is I and E. It will contain I and E, A. It will contain I and B. It will contain E and A. It will contain E and B. It will contain A and B. How many elements have we listed so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We must have 16 of them. So let's proceed. Now that we've taken all the singletons that are subset of this, we've taken all the duals that are subset of this, let us now go to the trios. The set that contains 3 elements. Let's go to the trios now. For the trio, the first trio will be IEA. Okay? The next trio will be IAB. The next trio will be EAB. Okay? Then the next trio will be IEB. So look at them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Now, if your power set, if C contains 4 elements, please check this later. The cardinality of C can be obtained as 2 raised to power the cardinality of C. The cardinality of the power set of C, is equal to 2 raised to power the cardinality of C. And that will mean 2 raised to power 4 elements that are found in C, and 2 raised to power 4 gives 16. Thank you very much. If there's any question, I will entertain questions now. Just quickly ask your questions before we call it a night. Okay? So we are going to stop there, and tomorrow's class on set theory, we are going to begin with set operations. In that class, we are going to be discussing operations like the intersection of sets, disjoint sets, complement of a set, intersection of a set. We are going to be looking at the difference between 2 sets, the symmetric difference between 2 sets. We are going to be looking at all those set operations in tomorrow's class. Thank you very much for joining the class. Please do well to share this video to all your colleagues and tell your colleagues about this class, that there is a class going on every day on MTH 101. And please go to my channel and look up the videos I made on STA 111. If you are doing STA 111, please go and watch those videos. They will help you because your exam comes up in January. Please start watching those videos to learn things from them. Even as you are supporting the channel, take note of the fact that this channel is meant to be a channel that helps you learn, and learning to write exams, learning to know, and also to pass your exams very well. So please share my videos from the channel to your colleagues. Share these videos. Thank you very much. Routine Okori, thank you very much. Oh, thank you very much. Share the videos, click a like on the video, and endeavor to turn on your notification button so that you get notified when we go live. I'm waiting. I'm going to wait 1 minute. Okay, two. I'm going to wait 2 minutes for questions. I need questions to come from you guys on all I have said today. And if there are no questions, I'm going to end this live class and we begin tomorrow with set operations. Okay? 1, 2, 3, 4, 5, 6. That's me counting. 7, 8, 9, 10, 11, 12. I'm waiting for questions. I'm waiting for questions from you. 13, 14, 15, 16, 17, 18, 19. Okay. So I want to believe that all I have said are well understood. So if all I've said so far are well understood, thank you very much for joining this class. Good night. Tomorrow we will meet again by 9 o'clock. Thank you, Precious Otu. Thank you very much. Routine Okori, thank you. I'll call you after now. Thank you very much. We are going to meet 9 o'clock tomorrow to continue our class. This time around, we'll be discussing set operations. Until some other time, good night and God bless you.